All right. So let me just take this thing out of the way. All right. So thanks a lot for the invitation. It's great to be virtually in Pittsburgh. I had a very general title for my talk, and I tried to fix it to be a little bit less general. So I started taking things here and there and all that, but then I gave up and I just went all the way for it. So I'm going to tell you a few things about neutrino physics. The goal is that I present you a few aspects of things that we are doing now. I'll focus on the liquid argon technology for the sake of it. And by the end, I hope you are excited about the future neutrino program in the US. So why neutrinos? Well, you all know why neutrinos. We don't know where their masses come from. We don't know why they are so lighter than the other forms of the standard model. We don't know if the neutrinos are Dirac or Majorana. The neutrino sector is the least known sector of the standard model. And if you think about it, the neutrino is kind of the darkest of all particles. It doesn't have charge, it doesn't have color. It only interacts via an interaction that at low energy is very, very weak. So this opens up lots of possibilities for neutrinos. Though in this talk, I'm not going to go into the theory of these questions. I'm not going to build a mass model, so I apologize in advance. I'm going to be more focused on phenomenology. So let's start talking about delta CP. Well, as Francesca just presented very nicely, P2K has measured the CP phase, and it's excluding CP conservation at almost 3 sigma. Now, the question is, fine, did we get it or not, right? And this is related to what Carlos Wagner has asked, that there is another measurement from NOVA which doesn't really rule out almost any value of CP, right? Actually, it doesn't rule out any value of CP unless it's on the inverted hierarchy. So for you to know what I'm talking about, just compare these two plots. So this is the CP sensitivity from P2K, and this is the CP sensitivity from NOVA. The x-axis here are slightly different. So this point corresponds to something like this point over there. And you see that although P2K has a preferred region, a closed preferred region, NOVA is everywhere. So that brings me to a very important point. Let's talk about cross-sections. Before discussing this plot, let's talk about cross-section. How do we actually measure oscillation parameters? Typically, this is a very, very simplified formula, but it suffices for us. When a neutrino changes from one flavor to another, it has an amplitude and it has a phase. And in this phase, the energy of the neutrino comes in, this guy here, right? So you need to know the energy of the neutrino. You need to infer that to be able to do oscillation physics. Now, how do we infer the neutrino oscillation, the neutrino energy? Well, if you think about a 2-to-2 scattering, let's say a muon neutrino comes, hits a neutron, gives you a muon and a proton, it is a 2-to-2 scattering. It's trivial to get the neutrino energy, right? Well, at this level, sure, but life is not that simple. What really happens is that when a neutrino kicks something, this something is typically inside the nucleus. And a nucleus is a complicated medium, right? So it has several nucleons inside. It has several effects which are not parameterized by perturbative physics. So there's a lot of non-perturbative physics going on. The initial nucleons are moving around due to forward motion, and so on and so forth. In some sense, reconstructing the neutrino energy, which now becomes a function of all final particles and the nuclear physics that goes on this reaction, is like trying to reconstruct a tomato from your ratatouille, right? I'm not sure you can actually do it event by event, but you can do it up to some extent. Now, what happens if you do this wrongly? This is very interesting because if you get the neutrino energy wrongly, you will distort the oscillation curve that you're trying to measure. And that will give you a different measurement, a different value for delta CP, for instance. So in this plot here, you don't look at the x-axis, that we have measured that parameter quite well. Let's just look at the y-axis. if you know how to reconstruct the neutrino energy well, if you're very accurate, not precise, if you're accurate, you would get this allowed green region here. But if you start missing some components, then this region starts moving to other values. So if you're not accurate enough in reconstructing the neutrino energy, you will infer, in some sense, the wrong value of delta Cp. Now, I'm not saying that T2K is wrong. Don't get me wrong, right? T2K does a marvelous work on constraining systematics and measuring the neutrino energy. But let's just go back to our delta Cp and discuss one more point before I stop there on a cross section. What I'm showing here, I believe Francesca showed these two plots actually in her talk. The one on the left is a by event plot from T2K. The one on the right is a by event plot from NOVA. The x-axis is the number of events for NUMU to NUI oscillation, so the number of NUI events. And the y-axis is the number of NUI bar events. If you fix all oscillation parameters, you are in a point here, say this little square there. And now, given all oscillation parameters fixed, you get delta Cp and you vary it from 0 to 360 degrees. And when you vary that, you draw this ellipse. These ellipses here are for normal hierarchy. The dotted ones are for inverted hierarchy. So let's focus on, let's say, this normal blue ellipse here. You see that T2K data sees more neutrinos than it should. Well, not than it should, but more neutrinos than what is expected for the standard model, and less neutrinos than what is expected for the standard model, even with maximal CP validation. And that enhances a bit their sensitivity to CP validation. This is not really a problem. That can easily be a statistical fluctuation, right? You see that the error bars are very close here. So it's not like there is anything super surprising there. Now, if you look at NOVA, this is basically the same plot. The data point is on top of the ellipse. And that explains why NOVA cannot pinpoint a value for delta Cp. Because the data point of NOVA is on the middle of the ellipse, essentially all values here are allowed. Now, there is no tension between this data, right, between T2K and NOVA. The statistics is quite small, so this could easily be statistical fluctuations. But given that these are different experiments with different materials, and cross-section plays such an important role, this is a very interesting thing to keep an eye on, and it's actually a very good test that we got the right CP validation if NOVA and T2K are pointing to the same direction. We are still not there yet, but we will be there at some point. So this, I guess this shows the fact that cross-section is an extremely important point. The neutrino nucleus cross-section is an extremely important point for the neutrino physics program, and is probably one of the biggest challenges that we have there. So we need to overcome this challenge. So before going to my next point, let me just tell you, I'm going to focus on liquid argon time projection chambers here. So let me just tell you what is a liquid argon time projection chamber, and then I'll tell you what is kind of the secret weapon that liquid argon time projection chambers have to overcome the cross-section challenge. So in a very, very simplified way, in a theorist way, a liquid argon time projection chamber is like a bubble chamber with calorimetry. So when a charged particle traverses the liquid argon time projection chamber, it ionizes, and then these charges are carried to some wires. It doesn't really matter for us in this talk. The point is you see a track of the particle, of the charged particle, only charged particles. And besides the track, you can measure the energy lost, and this gives you the calorimetry. So in some sense, it's like a colored bubble chamber, right? You have here an old bubble chamber event, and this is a new liquid argon TPC event, and you see that they are actually quite similar. The take-home message that I would like you to have from liquid argon type projection chambers is that it gives us access to a very rich topology of these events. And this is very special for this kind of detectors. For instance, here in the left, I'm showing you the the Argonaut plot showing that basically they can identify protons with only 21 MeV kinetic energy, right? So you see these tracks here can all be identified with particles, and liquid argon TPCs can actually see very low energy particles. Besides, topology carries information, and this is something that we are still exploring in liquid argon type projection chambers. For instance, I told you that a neutrino likes to kick a neutron, and the neutron becomes a proton. So, of course, this is ultra simplified, but if you have no nucleus, just this neutron going around, all events would have one proton, all neutrino events would have one proton in the final state, and anti-neutrino events would kick protons that have one neutron in the final state. Now, even when after you put the nucleus on it, you see that the proton multiplicity for neutrino events is peaked in one proton. And if you look at the same plot, which I don't have here, but you can find in the paper, the proton multiplicity for anti-neutrino events peak on 0 protons. So there is topology information that we didn't have before. And this is something that it's still, where this can take us is still being explored. So given that, there is a key aspect in for liquid argon TPCs that could allow us to overcome the cross-section challenge, which is redundancy. So let's talk about redundancy. I'll give you 3 examples of redundant measurements that we can do in liquid argon TPCs, which have been actually proposed very recently. So the first one is measuring the CP phase with low energy atmospheric neutrinos. So atmospheric neutrinos are produced when cosmic rays hit the atmosphere. They basically come from all directions. So here you have the Earth, and believe me or not, this is the Earth. You have neutrinos coming from all directions, and you have your detector. If you know where the neutrino comes from, you know the distance it propagated. And why is this important? Well, if we go back to oscillation physics, oscillation physics is an amplitude and some phase. It's a bit more complicated than that. There are interference terms, etc. But this is enough for this argument. The phase can be rewritten as this. And if you take the 2 delta m squares that we have, the 2 mass split in the solar one and the atmospheric one, there's a factor of 30 between them. So if you just fix a few parameters, say 5,000 kilometers, which is comparable to the Earth's radius, and a neutrino energy of half a GeV, and you plug these values here, you see that the atmospheric phase is about a factor of 30, and the solar phase is order 1, right? Which means that both atmospheric and solar oscillations have developed, and therefore you should have lots of interference, and that should be good to measure CP violation. So if you do the calculation for real, you get this plot here up, and you see that the probability for nu to nu compared to the probability for nu to nu changes as you change delta CP. So the dotted line here would be, a fixed delta CP, while the other line is, delta CP equals 0, while the other line is for a specific value of delta CP. And you see that the change here is roughly of order maybe 10 to 20%, which is pretty big if you compare to the beam CP violation. In the beam, because the atmospheric phase is large, but the solar phase is small, the nu to nu oscillation is actually quite small. And the effects of delta CP are at the few percent level, as you can see here, right? These are 2 different values of delta CP. So if you can see sub-GeV atmospheric neutrinos, you could actually do a measurement of the CP violation phase, which is completely independent of the uncertainties that we have in the beam. And that would be a great redundant measurement to make sure that we are getting the right answer. Now, if I say like this, it sounds kind of easy to do it. So why didn't we do it already? And the reason is actually quite simple. The experiment that has the best atmospheric neutrino sample is super K. But if a neutrino below the GeV scale kicks out a proton from a nucleus, this proton has less than a GeV of kinetic energy, and therefore it doesn't radiate Cherenkov light. So this proton is invisible. Now the correlation between this angle of the muon, say, or the electron of the lepton to the original neutrino direction is very, very small. So this makes impossible to reconstruct the neutrino energy and direction. And as I told you, oscillations depend on energy and direction. So at the moment that you cannot reconstruct that, your CP evaluation effects will be completely washed away, and you would need like megaton detectors to be able to see that. Nevertheless, liquid argon TPCs can do these low energy protons, and therefore there is a chance that we can reconstruct the neutrino original direction out of it. And doing the calculation, you see that if you suppose some true value for delta CP, looking at 10 years of data of DUNE far detector for atmospheric neutrinos, you could exclude several values of delta CP at above 3 sigma level. This is a very simple analysis, and we are working on updating this analysis to the full atmospheric neutrino sample. So that's one redundant argument. Redundant measurement. Let me tell you about 2 extra redundant measurements, and then we can move on to other topics. So the second one is measuring the hierarchy with atmospheric neutrinos. And this is actually a very, very interesting idea. So it is based on the fact that when you flip the hierarchy, neutrinos behave different from antineutrinos in matter. So if you could distinguish neutrinos from antineutrinos with atmospheric neutrinos, you would possibly be able to measure the neutrino hierarchy out of that without the beam. Now, in DUNE has no magnetic field, but there's something very special that is the muon capture process that could happen in DUNE. So the idea is this: a neutrino comes and produces a muon. The muon travels inside your detector and loses energy, and eventually comes to a stop. If the muon has a minus charge, it will typically be captured in the nucleus. And when it's captured, there is a lot of overlap between the muon and the protons in the nucleus, and it could be annihilated to, so you could have this process here: muon proton goes to neutron gamma. If it's a positively charged muon, then the nucleus repels this muon, and then it decays to a Michel electron, in this case a positron, and it's slightly different. It gives you a slightly different signature. Exploring this signature, you have a statistical charge ID in liquid argon detectors, and that would allow you to get the neutrino hierarchy at the 3 sigma level or so, depending on the true values of the other oscillation parameters. So that's quite interesting because it's a piece of physics that's independent from the beam. And finally, low energy neutrinos can actually interact with the argon nucleus in as a whole. So you have this NUI argon cross section that gives you an electron and an excited state of potassium. And you also have an excitation of argon that can be induced by neutrinos. And these 2 processes here could give you a measurement of solar neutrinos. So if you take the current determination of solar neutrino parameters that we have, you have that reactors prefer a value of delta M square, which is a little bit far from the solar measurement. There is no real tension there. This is a 2 sigma effect, but it's something to keep an eye on. And if you could do this measurement with DUNE and this tension, if this tension is something real, the pseudo tension, then you could have this displacement here, these 2 different regions of parameter space by the future reactor neutrinos and the future DUNE experiment. So these are very interesting redundant measurements that we can do at DUNE. And the key here is because the detector allows you to see more signatures and more topology than the previous detectors we have, combined with a large statistics. So given that we have all this redundancy and we have all these capabilities, we could venture into BSM territory. So let's talk about BSM. I'll be a bit brief here because of time constraints. So you have all heard about sterile neutrinos, right? So there is this mini-boon result, the recent result, somewhat recent, a year ago, which sees an excess of NUIs in a beam of nu mus. And the idea there is that your neutrino comes, produces an electron, the electron emits Cherenkov light. Whatever it produces together with the electron is kind of very difficult to see there, is a bit, unless it's a charged pion, it's invisible. But by looking at the shape of the Cherenkov ring, you can distinguish electrons from muons. There are several backgrounds, but these backgrounds also have to do with this cross-section measurement, that this neutrino nucleus cross-section that we were discussing about. But to make a long story short, there are a few experiments that seem to have seems to have anomalous results that could be, in principle, explained by sterile neutrinos. And there are several other experiments that do not see that. And summarizing, if you just separate experiments in two classes, and you see in the sterile neutrino parameter space where they prefer the theory, a class of experiments, the ones that have appearance of electron neutrinos, NUMU to NUI, would prefer this region here, while the other class of experiments, the ones that see NUMU disappearance or NUI disappearance, prefer this region here to the left. There is no overlap at 3 sigma between these two regions, which means that there is a tension. So this is old story, but microBOON may be able to distinguish some of these backgrounds from the low energy excess. So microBOON is an experiment very similar to mini-BOON, but with liquid argon. It's on the same beam line and roughly at the same distance, but the detector technology is a liquid argon TPC. And the nice thing is that microBOON can distinguish, in principle, electrons from photons, while mini-BOON can't. The photons will transition to any plus and minus pair, and that will emit a Cherenkov ring just like an electron in mini-BOON. In microBOON, there is a different signature. The point is, we will have some very good new information on this kind of excess here, the nature of this excess, hopefully by Neutrino 2020. So stay tuned. But what I want to say about BSM is that this is not the only BSM that can be done in these neutrino experiments, especially in liquid argon time projection chambers. There is a whole lot of BSM scenarios that could be probed there. Some of them would involve heavier states, for instance, the heavy neutral leptons, for instance, right, where you produce a heavy sterile neutrino that can decay down to neutrinos and charged leptons, etc., or pions, magnetic moment, neutrino tridents, and so on and so forth. There are way too many BSM models for me to cover here, but let me focus on one case. So let me focus on the case of low energy models, right, low scale models. So to do that, I'll focus on a specific model. So imagine that for some spurious reason, you decide to gauge the B minus L of the third family. Sure, you can always do that. But imagine that not only you do that, but you say, now let me try to push this gauge boson mass, this flavor violating gauge boson mass, as low as possible, right? You would imagine that usually flavor physics constrains scales at the 1000 TeV level. So you would imagine that you cannot push it so low. But actually, what happens is that you can push this gauge boson mass below the GeV scale. So here I'm showing you a plot of the gauge boson mass for this B minus L of the third family and the gauge boson coupling, the gauge coupling. And you see that for coupling of order maybe 10 to minus 2 or a few 10 to the minus 2, you could have a mediator at the 1 GeV scale, and there would be there would be very few constraints, right? This would be allowed. And this is very interesting, not only because it proves our ignorance about low scale physics, but it also shows a nice complementarity between several observables of different experiments. For instance, here in this plot, I'm showing you bounds from K to pion decays, these blue regions here. The red region are bounds from neutrino oscillation physics. So if this is a gauge boson of the third family, it couples more to tau neutrinos. And because it couples more to tau neutrinos, it induces a new matter potential that can change atmospheric neutrino oscillations. So you have the constraint here from neutrinos, you have constraints here from DD bar oscillation, upsilon decays, and so on and so forth. So this shows you a large complementarity of vastly different experiments that play in low scale models. And recently, you can check the talk by Sudeep Jana. It was one of the parallels yesterday, I guess. We have analyzed the complementarity between these low energy observables and high energy observables from the LHC. So I show you here the mass of this new gauge boson. I changed the notation to be confusing, but Z prime is this X, doesn't matter. And this is a parameter that we call the non-standard interaction parameter. It parameterizes the strength of these interactions compared to the weak interactions. So one would be very, very similar to the weak interactions. This black region here would be the low energy observables. The red one is a paper by Elahi and Martin, where they did a dedicated search looking for BB tau tau. And up here, you have the general monojet searches at the LHC. And you see that at every region, there is a complementarity between these different observables. So that's quite interesting. Now,
just a quick reminder, you have about 5 minutes left.
Sure, yeah. Now, a general characteristics of these models, these low energy models, is not in all models, but is in a large class of models, is that your gauge boson mix with the Z. And this happens, it's very simple to understand. You can imagine that in the standard model, our Higgs boson is charged under SU2 left and U1 hypercharge. And because it has these two charges, the original, let's say the initial B and W3 bosons mix and form and give you the photon and the Z. If you have another gauge boson with an additional charge, then the initial B, W3 and whatever new gauge boson would mix to give you photon Z and Z prime. And the Z prime mixing gives you something that enhances parity violation at low energies, which could actually show up when you try to measure the weak mixing angle at low energies. And this is an interesting paper by Human, who's given a parallel talk at some point, I think, and collaborators, where they show that if you have a mediator that is light enough, high energy measurements of theta weak would not be affected, but low energy measurements would. Now, it happens that we could try to see this at the DUNE experiment. So how would we do that? Well, we would need to try to measure theta weak. And this brings me to the last point of this talk, which is precision physics in this future detector. This is just an example, but I'm pretty sure there are other neutrino physics observables that can be measured in liquid argon TPC. So Francesco told you about the DUNE near detector complex, and it's a very rich complex. It's very interesting. And there is one point that I want to highlight, which is the concept of this DUNE prism detector. So DUNE prism, you have the neutrino beam and you have your detectors here. There are other detectors here, but let's forget about them right now, only for this talk, this slide. The DUNE prism concept is that you can move your near detector perpendicular to the beam line. And what this gives you is that at every different position, this detector sees a different neutrino flux. But the correlations between these different fluxes depends only on kinematics. So this is a very nice way, a nice idea to try to get rid of systematic errors like hadron production in the beam, right? When a proton hits a target, you need to know how many pions come out. That's non-perturbative physics. That's very difficult. So you need to be smart to be able to eliminate systematic uncertainties. So what we are looking at here is, what if we use this, but we try to measure the weak mixing angle at DUNE? So our signal would be a neutrino scattering on electrons. And the nice thing about neutrino scattering on electrons is that this is a very clean event. It's just one electron track in a very forward direction. And there is kinematics linked to this quantity here, basically the energy of the outgoing electron times the angle with respect to the beam line square should be smaller than about an MeV. There are backgrounds to this search, and I'm not going to go into these backgrounds into much detail, but the idea is that you can create electrons with the usual quasi-elastic scattering. And although you can kill lots of these backgrounds, the cross-section for this is enormous. And the other possible background would be you can create a pi zero with very little hadronic activity that you will not see. And this pi zero decays to two photons. One photon behaves like an electron. The other photon could just go away or be too low energy that you don't see that. Making a long story short, if you use that, if you use the DUNE prism technology, looking at this signal and considering these backgrounds, this is what you get for the measurement of theta weak. To be honest, in this measurement, we assumed that the backgrounds were negligible, but we are updating that to more realistic backgrounds. So this sensitivity will get slightly worsened, perhaps a little bit more slightly, but let's see. But the interesting thing is that you could add a neutrino measurement of theta weak at low energies, and this would be a nice addition to this plot, since the only neutrino measurement that has competitive error bars in this plot is the NUTEV, which is about 2.7 sigma away from the expectations. And although there are many discussions about why NUTEV is away, it is something to keep in mind. In any case, this is an example of precision measurement that you could do in the liquid argon TPC. So let me conclude. The future neutrino program in the US, the liquid argon neutrino program, will have very high statistics, will give us access to new observables that we did not have access before, especially with this high statistics. We'll have, this will lead to better precision in the observations that we do, and it leads us to new opportunities. And in fact, these new opportunities are still unexplored. We still don't know exactly how much can be done with this liquid argon TPCs. So I would invite you to think about it. And in doing that, it's obvious that theorist-experiment collaborations are very, very much needed, because you need to understand the detector capabilities, but you need to come up with new ideas and new, for instance, new BSM scenarios that could be measured in these experiments. So I apologize that I could not cover many interesting topics like astrophysics, cosmology, yeah, et cetera, but I didn't have 2 days to speak. I only had half an hour, but I'll be around to chat. If you want to chat, ping me on email, and I'll be on the meeting rooms that Tao is organizing. So thank you.
Thank you very much, Pedro. Very nice. Other questions from the audience? I don't have any in the Q&A. Yes, oh, they are coming. There's one from Ahmed Ismail. How much variation is there among the momentum thresholds of different LAR TPCs? And is it possible that these thresholds could be reduced further? For example, between now and when to turn on?
That's a very good question. So what sets the threshold is 2 things. So the charges are carried down by electric fields, and they are read in some wires. And these wires have background, right? Has like noise. So one of the things that set this threshold is the noise. This is very, very low threshold, right? The noise for these things, for instance, the argon had this paper with the blips where they could see energy positions of half an MeV on these wires. But there's another thing that sets you this threshold, which is, you see, you want to look at the dEdx, the amount of energy a particle loses when it travels. So you cannot do that with a single wire. So you need a particle to travel at least a few wires. I mean, exactly how many is an experimental question. You could imagine 3, 10, 20. But if you want to reconstruct the particle and ID it, you need this particle to travel a few wires. So for instance, I believe Microboon had done an analysis where they had sensitivity starting from 40 MeV protons, 40 MeV of kinetic energy of protons, where these guys would travel 20 wires. I believe this is the right number. I may be wrong, so you need to check with the experimentalists. But that is the way you would reduce these thresholds is by applying smarter reconstruction techniques or by reducing the wire spacing, although that would cost money.
Okay, thanks a lot. There's another question by Carlos Wagner.
So thank you for the previous speaking to you, Pedro, for the long energy geometry. The low energy said that mini-boon happens at energies at which one would naively expect that nuclear effects should be important. How much attention should we pay to it? Given that the Microboon experiment is working very hard on solving the nature of the low energy mini-boon excess, if it's due to electrons or photons, and we might have an answer by neutrino in like 2 months or so, or maybe a month, you should pay a lot of attention because it's just a month of a lot of attention. Now, I agree with you that there is nuclear physics going on there, but there's lots of smart people working on it. There's lots of data-driven backgrounds in the mini-boon analysis, and nobody could ever come up with an answer. So I think even for the sake of understanding the low energy nuclear physics, it would be interesting to explain mini-boon, even if there are no sterile neutrinos.
Okay, one last question is there by Yongdu. Can you comment on the advantages of DUNE over the low energy measurements such as Möller and MESA P2 and the high energy measurement at the HLHC?
Well, the advantage is, if you see here, DUNE is not more precise than these guys. So the advantages are that this is a different observable. So in some sense, it's redundancy. The reason why we have so many data points in this plot is that we want to see redundancy there. And you could imagine that there could be new physics that couples more strongly to neutrinos than to, say, protons and electrons. If that's the case, you could see a deviation in the weak mixing angle, a larger deviation with a neutrino beam than with, let's say, a molar scattering experiment, right? At low energies, electroweak symmetry is broken. So you could imagine that you're in a scenario where EFT doesn't apply, and therefore the coupling of electrons to a new gauge boson could be much weaker than the coupling of a neutrino to new gauge boson. This kind of study is very general, so you cannot see it from this kind of plot. But it would be very interesting to try to constrain theta weak at a level similar to our best observations, but using neutrinos, since there is way more freedom to come up with new interactions in the neutrino sector.